In this particular reaction, the ratio of reagent to product of butyl chloride to butanol is 1:1. For each mole of butyl chloride that gets hydrolyzed, 1 mole of butanol is formed. The rate of disappearance of butyl chloride is the same rate as the appearance of butanol. So in this case, the rate of disappearance of the reagent, butyl chloride, is the same as the rate of appearance of the product, butanol. And that is because the reaction ratio is 1:1. 1 mole of reagent to 1 mole of product are formed. I'm going to ask you to stop the video now and perform a little calculation. You've got here a graph representing the reaction of hydrolysis of acetyl salicylic acid, aspirin, into salicylic acid and acetic acid. And it just shows the change of the concentration of the aspirin and the salicylic acid over time, over a period of 300 hours. The rate, because the reaction is 1:1, for each mole of acetyl salicylic acid that is hydrolyzed, 1 mole of salicylic acid gets formed. The rate of disappearance of salicylic acid is the same as the rate of appearance. The rate of disappearance of acetyl salicylic acid, is the same as the rate of appearance of salicylic acid. So I can call this A, the reagent, the acetyl salicylic acid, and B, the product. So I'm going to ask you to stop the video and calculate what would be the average rate over the first 50 hours of reaction. So what would be the average rate of this reaction during the first 50 hours? Stop the video now, please. So I hope that you stopped the video and had a go at the exercise. How would I go about doing this? Well, if I choose, for example, to calculate the reaction rate with respect to the formation of salicylic acid, then I would simply look at the values at 0 and at 50 hours of the concentration of salicylic acid. So at 50 hours is roughly 1 10 to the minus 3 molar. At time 0 is 0. The reaction hasn't started yet, and the time period is 50 hours. And I have a rate of 2.0 10 to the minus 5 moles per liter per hour. I could have chosen to calculate it with respect to the formation of the disappearance of acetyl salicylic acid. And that would, in this case, because of the graph, would be slightly more difficult, just because the graph doesn't give you enough resolution to find out what those numbers are there. What is the concentration of aspirin at 50 hours and at 0 hours. But if you use the original data that was used to put together that graph, you would see that the concentration at 50 hours is 4.7 10 to minus 3. The concentration of aspirin at 0 hours, the initial concentration, is 5.7 10 to the minus 3, and again the period is 50 hours. So you end up with the same value, because the rates of formation of salicylic acid is the same as the rate of disappearance of acetyl salicylic acid. What about if the ratio is not 1:1? For example, in this reaction, we have 2 moles of hydrogen iodide that produce 1 mole of hydrogen, molecular hydrogen, and 1 mole of iodide, molecular iodide. So 2 moles of hydrogen iodide will disappear for each mole of H2 or I2 produced. The rate of hydrogen iodide disappearing is twice the rate of hydrogen or iodine being formed. Or if you want to express it the other way around, the rate of formation of hydrogen or iodide is half the rate of disappearing of hydrogen iodide. So stoichiometric coefficients in the chemical reaction influence the reaction rate. In general, if you have a reaction of the type reagent A plus B to produce reagent C plus D with their particular coefficients, you can express the different reaction rates with respect to each reagent or each product in this case with the reagents with a minus because the concentration is decreasing, as 1 upon the coefficient for that particular reagent or product. So this is a general way of expressing a reaction rate with respect to a particular chemical in a chemical reaction.